I'd like to welcome everyone to the Wednesday morning session of the Brown 2026 AI Winter School for the Center for Fundamental Physics of the Universe. I'm Jan Del Antonio. I'm the Associate Director of the CFPU. And I'd like to introduce this morning's presenter, Brian Ostiak from Microsoft Labs, who will lead a workshop on physics-informed neural networks. So Brian, thank you.
Yeah, thank you. Thanks for the invitation and for being here. Yeah, it's just a little bit about my background. I did my PhD in theoretical particle physics at Notre Dame, and then did postdocs at the University of Oregon and at Harvard University. I was working in sort of the phenomenology between theory and experiment. And I got progressively more and more interested in figuring out how to use machine learning to search for dark matter, both at collider experiments and at space telescope observations. I eventually joined Microsoft in 2022. In Microsoft, I work on the Industrial Solutions Engineering organization, which is not a research organization. It's a little bit more on consulting-ish, and we work with customers and help them scope out their AI and machine learning problems. Right now, it's building a lot of co-pilots, but we do things with computer vision, forecasting, and all of that. And so I think that the what we get as physicists really helps well with these. And my co-presenter is actually not going to be here presenting, but Darsh Kadwani also got a PhD in theoretical physics from Oxford. And we met as he was a data science manager and industry solutions engineering as well in Microsoft. And the area that we tend to work in now is trying to apply machine learning for science and how we can do this with some of our large customers. And so we're part of a group that was specifically trying to look into that. And Darsh has now gone on to join another company that's specifically focused on machine learning for science. And with that, was not able to join us. But I wanted to include him here because he developed a lot of this material as well as we were doing these presentations for internal Microsoft. And so I want to lay out just a little bit of where we're going to be going today during the session, and specifically point out that as Darsh and I are both physicists now working in industry, we're excited to be here to talk at the Brown Winter School. But before we begin, I have to note that the physics-informed neural networks, or PINs, that we're going to be talking about were introduced by a research group at Brown, and much of the foundational work we're going to reference comes from that community. I want to be explicit here that the research that we're going to discuss is not original work that Darsh or I did. We're teaching these ideas from an industry lens, and we want to help you apply them in practice. And so our aim for the session is to be practical and conceptual. By the end of today, I hope that you'll be able to think of loss functions as explicit assumptions about noise, priors, and physics. That you'll be able to parameterize solutions so a single network can represent a family of problems. Which should be able to set up and interpret inverse problems where parameters are learned from the data, and to view all of this to be able to build fast surrogate models that let you explore a large parameter space without running high performance computing code for every sample. There's going to be a mix of different lectures and a couple of different lab sessions. And so hopefully you'll be able to get hands-on and ask any of the questions as we go along the way. And I do want to emphasize that there's going to be some trade-offs on how to balance data versus physics terms, how boundary conditions apply, and pins are not always going to be the best solution going forward. And I'll get into that a little bit in our wrap-up. But I think there's a lot of really good pedagogical information that as we understand this, it should really open up how you view machine learning in the physics regimes as we go. All right. So before I really dig in, I want to first give you a review of some of the super fundamentals of fitting data, just to ensure that we're all on the same page, talking the same language. These next few slides are going to be from when I was just starting to get into machine learning about 10 years ago. And I clearly have a typo in there. But so this is going to review, represent how I saw machine learning as a physicist. And so first, let's say that we want to fit some data, and here I've got something that looks pretty linear. How are we going to go about fitting data? Well, the easiest thing to do is first to plot the data. Here we see that it looks roughly linear, so we're going to define some function that has a constant and a linear term. And then we have to decide, how do we know, how can I fit A0 and A1 to get the best fit? And so we have to define a loss function. And often when we're doing linear regression, we use the mean squared error. And so for this, we're going to take our prediction, our function, and subtract that from the actual value and square it. Why do we square it? Well, we square it because we want to not have an error in one direction and an error in the opposite direction cancel each other out, right? And so this is the general way that we are taught to fit data. And the way we go about then figuring out the values of A for the function is we minimize this loss. And so the best values are when the derivative of this goes to 0, right? So this is how we were probably all taught to fit data. And of course, sometimes we might end up with something where maybe that's not quite linear. And how do we know? Is this point in an error, or is this actually some sort of quadratic? Well, if we want to do this, if we think this is a real data point, we can always add in another term, right? And so I'm jokingly called this quadratic regression, but it's still just linear regression. We have our new function now, and we're going to do the exact same process. And we can find the best fit. And maybe it looks like this. And of course, the question always comes about then of, well, we're missing some points. How do we know that this should be quadratic? Why don't we add in even more data points, right? And so, we always have to be cognizant of what is the model we're actually trying to do. And especially as we go into machine learning, we're going to usually heavily over parameterize our models. And so we need to know how do we make sure that we're fitting the data appropriately and not overfitting to the data. We want something that will generalize and that our extrapolations won't be crazy like this. Okay, so that's for fitting numerical numbers, but what if we want to predict a class? So the typical thing that you would see here is, say, something like cats versus dogs. When I was doing this, I was, again, in high energy physics, and so we were one of the key areas of interest was trying to figure out if a spray of particles at the Large Hadron Collider was coming from a top quark versus one of our other quarks. And so just as some simple version of looking at this, say that we have some observable. It doesn't really matter what it is right now, but we can make it so that it's separable. And so I've got all of one class is here and another class here is, and maybe there's some regions where it's a little hard to tell what to do. So we want to predict, in this case, x's versus circles, and those aren't really numerical. So what can we do? Well, the easiest thing is to define one of them as 1. So we're going to call our signal as 1 and our background class is 0. Okay, that's great. So now we have something that looks like maybe we can fit it with data. So what are we going to do? Well, we could try to do a linear fit, but now maybe we have values of like 0.2 or anything like that. Like, what does that really mean? So that's not really mapping to our labels of 0 or 1. You could round it to the nearest number. This looks like it's maybe a decent fit. But again, the next question is, well, how is this going to generalize to new data? So what happens if we get another data point now and the observable is even higher? Does that mean it should be a label 2? That doesn't really make sense. And so the point you should take from this is that this is not the right way to go about doing a classification problem. So instead, we use logistic regression, where we're going to feed the data through a sigmoid, and the shape of the sigmoid looks like this. Sorry. And so the key point here is that when we take that basically that same function that we just did, and now feed it through here, where z is going to be the value that we were outputting before, it's going to map it so that large negative values go to 0 and large positive values go to 1. And we're not adding any parameters. We're just changing the shape of the output. Okay, so now that we've got this, the next question is if the mean squared error is still a good loss function. Uh, and by that, we want to think about, well, in the mean squared error, we wanted that, that we were that a positive and a negative errors didn't cancel each other off. That's why we squared it. So we could still do that. That makes sense. But what does it mean for a prediction to be very far off? In mean squared error, if we predict if the value we were expecting is 100 and we end up with 1,000, the error there is large and we're squaring it. So it's penalizing uh, residuals that are large even worse, right? And well, can we do that in if we use mean squared error with this? And the answer is, again, not really. So we're going to end up changing our loss function to help penalize far off more. And so the way that we're going to do it is we're going to view that our prediction now from our network after we've fed through the sigmoid, we're going to take the log of that. And this is the binary cross entropy. That is often used for classification. So let's just take a quick look at what this says is that, again, yi is going to be either 0 or 1 for the class. So if we were predicting during our training a, a case that was actually part of our signal, yi would be 1, so we would just ignore this term. This term would go to 0. And if our prediction is very close to 1, the log of 1 is going to be or log of close to 1 is going to go to 0, so that's going to minimize our loss. But if we were predicting something closer to 0, the class of saying that it's background, now we get a large error here. And the logic is the same over on the other side. If we're predicting background, or if it's a true background, but we're predicting the signal, we get a large error here. Right, so that's the basics of this. Is we want to be able to heavily penalize things that are far away from the actual prediction. All right, so this is how I was thinking about these when I was first getting into machine learning as a physicist. Sorry, I guess we can continue this example just a little bit further to see. In here, we've got our prediction is now going to be, we're feeding it through the sigmoid, and we've got the prediction of x and a. And so the question is, well, what is this model that we're fitting now? And so we can do the same sort of thing. So if we have this data here where we've got two observables, x1 and x2, and now I've got my signal is in one corner and my background's in the other corner, I can still use a model that looks like this. So it looks similar to our linear regression. So I've got a constant, a term that depends on my first observable, a term that depends on my second observable. And we're just going to try and fit A0, A1, and A2, feed it through the sigmoid, and we get a training that looks something like this. And so we're hoping that we're going to get large values of our prediction, which is going to then map to the signal class up here, and large negative values over here, which is going to map to our 0 class, our background. And when we train, we see that the model is going to do that. And so we get a boundary that says that this is where sort of the overlap is, right? And so very simple case, but just to make sure that we're all trying to think about the classification and regression problems the same way. Again, as we did with the quadratic, there can be shape in our data. We can add in quadratic terms if we see that. So here on the left, I'm going to not add in quadratic terms. On the term on the right, I'm adding in quadratic terms as my model. And we can see that as we fit these, getting out the different values of our A's, of our coefficients, is going to change the shape of the data or of our decision boundaries. Okay, so again, same thing when we get into classification, we also have to worry about overfitting. How do we know how many parameters to add and all of that? Yeah, I see there's a question.
Yeah, Brian,
Yep.
there's a question from one of the attendees that asks about neural networks and how they can handle stochastic variables. Are there things that where the number of variables or the nature of the variables are not the same in every case?
I'm I guess slightly confused by it. So like In a neural network, what we're going to do is have our coefficients here are going to be what's fit. So these are going to be like the weights and the biases of our neural network. And the variables, I assume we're talking about what I'm calling observables here. So if there's some randomness there, yeah, there's different ways that we can try and account for that, especially if we get into more complicated modeling scenarios. You can actually have the weights here that you would get, the A1, A2, A3, you can actually model those as Gaussians themselves if you want to. And so rather than taking a very specific value, you can build stochasticity into those and try and learn what the mean and variance of those needs to be to fit the data the best. So I'm not sure if that's exactly what the
I
question is.
think that's exactly the question.
Okay.
Thank you.
Yeah. So there's ways to do that. I'm not going to get too much into that at all into this, but yeah, there's definitely ways to do that in the modeling. Variational autoencoders are this is typically done there. It's a very different use case, but you can take that same logic and apply it to any other sort of regression problems as well. Yeah. Yeah. Thanks for the questions. Yeah. Please post any questions in the Q&A. I want this to be helpful for everyone. So yeah, I welcome questions throughout. All right. So just as our recap of all this, we can use basically the same process for fitting a curve or a classification. What we have to do is define a cost function or a loss function. It's easy to add parameters, especially if the shape is unknown, but then we do have to worry a little bit about potentially overfitting. And if there's lots of different inputs and the shapes get complicated, the number of parameters can grow very, very quickly. Okay, so that's just making sure that we're all on the same page on how we fit data. Now, if we jump forward a little bit as we go to neural networks, so everything we did before was not a network, that was just fitting a specific model. When we go to networks, why do we do that? It's because they can approximate any continuous function, and so this is the universal approximation theorem. And the way that it does this is we train the network on many examples. So as we saw, we have our observed data, and we fit it to the data. When we do this, we have to be careful of what our output or the activation is. So when we were fitting our numerical data, we had just a linear activation. When we had the classification, we used a logistic or a sigmoid. And so that our data was between 0 and 1. And when we do that, we also have to be careful of what the loss function we choose. So mean squared error versus the binary cross entropy. And so, again, 10 years ago when I was looking at this, that all made sense from a practical reason of why we choose these losses. But what I want to dig into now is, well, where do these losses actually come from? And what assumptions are we really making about the data when we do this? So I'm going to jump back to the regression problem and look at just what are the actual assumptions that we're making. So when I have this plot over here where I've got some data that looks roughly linear, and I say that I want to fit this to a line, I'm not trying to fit every point exactly. And so what I'm doing is I'm assuming that the data is distributed with some Gaussian noise, right? And so yeah, that there's some noise in my measurement. And so if I want to write down what the probability of observing my value given some model, I can write this out as a Gaussian, right? So I'm literally putting in the Gaussian noise. So I'm going to make my prediction. So my prediction here is f of theta. So whatever my function is, theta is whatever the internal parameters of my model are. Before it was those A's. This could be the weights and biases of a network, whatever it might be. And X is my input data. So I'm going to make a prediction and compare it and put in just the Gaussian likelihood here. Now, when we fit our data, what we're really doing is maximizing the probability of our observations, right? Given the model that we're looking at. So by changing the weights of our model, we're maximizing the likelihood, one way to do that easier is to take the negative log likelihood and then we minimize that. So if I take this Gaussian probability and take the negative log likelihood, I get, take the log of this, I get the Gaussian width here, but then really I've got the y minus the prediction squared plus a constant term. And this is really just the mean squared error. So, we can drop off these as we're minimizing it, and we're left with just the mean squared error. And so when we are fitting a regression data, the intrinsic assumption that we're actually making is that we've got Gaussian noise around our predictions. Okay, so that's sort of an interesting thought process of it's not just that we want the positive and negative to not residuals to cancel each other out, but there's actually a statistical reason for why we're choosing this. And same thing actually if we go to our classification model now. And I know this is relatively small, but when we have data that's in two classes, this is actually essentially modeled as a Bernoulli distribution, which is a binomial distribution where we only have one observation. And so if I want to write out what the probability of observing a 1 or a 0 given my the data in my model, the way we can write this out is the probability of the prediction minus 1 minus the prediction, and so is the classic just bimodal distribution here. And so this is what our model actually is. And so now when we again want to maximize the likelihood over many observations, we can maximize this, or instead take negative log likelihood and minimize it. And now we get exactly the same binary cross entropy. And so when we do a classification problem and train with the binary cross entropy loss function, what we're intrinsically doing is assuming a Bernoulli distribution, and that our the predicted values that we're outputting should be the probabilities. So the probability that it belongs to the signal class is actually what we're making the prediction on. Right. So again, this is hopefully taking it from not just, well, here's how I do it in code, to what does this really actually mean? So as a recap to this, then the loss function tells the network what good means, and different assumptions that we put into this lead to different behaviors. And so when we're coming up with a problem and we want to model it in some way, we're really encoding the assumptions that we have about the data into how we're going to fit it. And so when we so that's the statement. So how do we actually go about doing this? So I've said we're going to minimize the loss or maximize the likelihood. Most solvers for this do it using gradient descent. So we're going to take whatever our function is in our data, and we're going to take the derivative with respect to any of the model parameters. And that tells us what direction is going to lower the loss, and we take a step in that direction. Then we're going to repeat this over and over again, right? So that as we're doing any of this, one of the other key features of our loss functions is we want it to be differentiable so that we can minimize it easily. Okay. So that was background on just what our losses are, where they come from. Now let's actually finally get into a physics example. and what I want to look at for before we get into the first lab is the simple harmonic oscillator. I know this is a problem that we probably have all seen and studied way too much. Harmonic oscillators are everywhere in physics. And so we're going to do this first from the point of view of just Hooke's law. So we're going to have F equals ma with the spring constant with the restoring force. The solution to this is, of course, that the position as a function of time is going to go as a sine or cosine. Here, I'm just going to map it to a cosine, where we've got an amplitude, which is the maximum displacement, plus a phase. And then omega is the angular frequency, how fast it oscillates, which is determined by the spring constant and the mass. Okay, so I know we've all seen this before. Just to make sure that we're really talking the same page. The amplitude is going to be again the maximum displacement. The period is the distance between, or the time it takes to get to the same spot. And so what I want us to do is to figure out, okay, if I have some data that looks like it's oscillatory, we want to fit the simple harmonic oscillator with a neural network. So thinking through everything that we just talked about of how we're going to design our loss, how we're going to even design our network, like what do we actually want to do when we're doing this? Yeah. Uh,
And
we,
just a
yep.
question going back just a
Yeah.
couple slides.
Yeah.
When you calculate the loss, you showed that the mean squared error looks like a Gaussian probability. There's a question about whether there's a what's the equivalent or whether there's a use for using absolute value of difference rather than square. And what
Yeah.
assumption does that map to?
That's a great question. I have seen absolute value used before. Um, I don't remember what the assumption is on that. Um, I've normally seen that done more phenomenologically. People saying, "Oh, well, it's penalizing. It's worrying too much about the outliers, and I don't want it to do as much there." And so then they choose to do um, the absolute value instead. Um, from
There,
another point of
there,
view, it can be
there is an issue in differentiability, right? When
yes,
you get to
that's
zero.
exactly what I was going to say as well too. So, but I have seen it done. I know in one of our papers we found that we were getting better fits and better results if we did that. Uh, but yeah, what is the actual assumptions that's being made there? I don't remember, and I'm not
Okay.
sure if there's a great answer to that, but there might be. Uh, yeah, yeah, it's a great question. Uh, Okay, so if we want to fit this data, what we're doing is x as a function of time. So our network here is going to be a very simple network. We're going to have just our input is time. So we're going to have one neuron as our input. We could have multiple hidden layers with many neurons. That allows us to fit this nonlinear data well. So we probably, as we've learned throughout, that neural networks do want to have multiple layers, and the more layers, the sort of more you can fit. But also width helps as well, right? There's always this width versus depth discussion. And the output is just going to be the position as a function of time. So we're just going to have one neuron as our output. Uh, I've chosen our amplitude for this right now um, to be one. So our data is in the range of -1 to 1. So even though I said that we normally would, when we're fitting data, pick the activation to be linear. In this case, I'm going to use a hyperbolic tangent because it's also bounded from -1 to 1. Uh, and so that's just going to be what the range is output, just to make things easier that way. That's going to be for the output activation function. For the interior, you could really use whatever you want at this point. Later, we are going to want to use a hyperbolic tangent, and I'll get into that once we get into the physics-informed neural networks. And it doesn't have to be a hyperbolic tangent, but normally, at least back when I was still in physics, we would always use ReLU or some version of that as our activation function, which works really well for fitting data, but it's going to not work as well for pins. And again, I'll get into that. And again, we're fitting this. We're not doing classification, so we're going to use the mean squared error and assume that we've got some Gaussian noise around our observations. And so when I go to fit this, I'm going to look at what my loss is over here. And so it starts off, it takes a little while to learn, and then it quickly figures out how to fit this data. And we see that it doesn't know how to really fit the function. It's fitting this data, uh, but because we don't have data out here, it's not generalized well at all. It's not extrapolating well. So I would say that this is a case where the vanilla neural network is failing. It does really good on the training data. If we had validation data or test data in the same range, it would also do really well there. But it does not do well to the data outside of where it's seen. It does not generalize. Um, so how can we make this do better? By adding in physics assumptions, not necessarily just statistical assumptions. What we want to do is, as I said before, the losses are encoding assumptions about our data. And so the key insight from the group at Brown, looking at these physics-informed neural networks, is that we can feed our known physics directly into the loss function. How we do that, oftentimes we have to have some parameter to scale how much we worry about the fitting the data versus how much we worry about fitting the physics. Um, so we can parameterize our loss this way. And the question is, well, what physics do we know about this? Well, in this case, we know for the simple harmonic oscillator, we know what the equations of motion are. We might know that we want to have very specific boundary conditions or initial conditions. And so we can put these directly into the loss and punish the model for large residuals on these known things that we want to be fitting. All right, so let's dig into how we can do this and what this might look like. Yeah.
Hey, Brian, before you do,
Yep. Yep. Absolutely.
you mentioned activation functions. There's a question about
Yeah.
the role of the activation function and what assumptions are encoded in the choice of activation function.
Yeah. So the biggest thing about an activation function, and there's lots of research on this, and the hottest greatest activation functions do change as we go. But the biggest thing about an activation function is that we need to add some nonlinearity into it. So when we're building a neural network, when we have our inputs, if we only have linear transitions, we're doing basically linear algebra, and when we get to our output, if we don't add in any nonlinearities into there, we can only do linear fits to the data, no matter how wide or deep we make the network. And so by adding in some form of nonlinearity, whether that's a hyperbolic tangent, the ReLU, anything that's nonlinear, that's what allows us to fit more complex data. Now, there are caveats to all of that, and that there's more considerations that we want it to be differentiable to make things easy. So we don't want just random nonlinearities. So the ReLU is I've got a slide. Let me. I'm not going to jump ahead. The way I have to click through, it's going to be a little too hard to get to there. I've got a slide on what the ReLU looks like for those who, if you're not sure what I'm talking about, but it's essentially it's a stepwise function or piecewise function that's zero if x is less than zero, and it's a slope of one, a line with slope of one if x is greater than zero. So the derivatives are very easy to compute there. It's one or zero, and other than at the kink, and so yeah, that's easily differentiable. And then the other thing that we want is that the gradients don't vanish. So as we build up to a very large network, as we're taking our derivatives to find our gradients, if we're using something like hyperbolic tangent, usually that was historically what was used for a long time. And as the networks got deeper and deeper and deeper, if I go back to just the plot of the sigmoid, I guess so sigmoid's another so if I look at this plot here for the sigmoid, hyperbolic tangent has a very similar shape. So both these are often used. That if we start getting really far out on here, the derivatives are essentially going to zero on both sides of these. And so the deeper the network gets, you can end up with what's called like a vanishing gradient, that essentially you're on these tails for so long. And when you're multiplying, doing the chain rule, you essentially end up with no updates because there's just so small that way. So so all that's very long-winded to say that there is some art in picking what the activation function is. The main point of the activation function is to add nonlinearity, but then we also want to make it differentiable, and we want the gradients to be able to pass through the network well. Okay. Yeah, there was a lot there. Please ask more questions if you've got them, or we can ask them during the lab session as well too. Okay, so what we want to do as we go through and try and add the physics into the loss function here. So as I was just saying that well, when we're training our network, we've got our loss, which is a function of, in this case, I'm only writing it as a function of the neural network parameters because our data itself is fixed as I'm viewing this. So right now I've just got the mean squared error. And when we're doing our optimization, we take the derivative of the data with respect to the neural network parameters, and which is just given by this term, and we take our our new network parameter is going to be the old network parameter minus the loss or the learning rate times that gradient evaluated where we're at. Right. So really, we're just taking the gradient and taking a step in that direction. Right. And so uh, what's allowed a lot of this to go forward faster now is that all of these frameworks will take care of this differentiation for us. We don't actually have to go and write out what all of the, as we change our network architectures and all of that, we don't have to go and compute these derivatives by hand anymore. Okay. So when we're doing this for our simple harmonic oscillator, uh, we know that the harmonic oscillator should follow these equations of motion. So what we can do is say, let's define the physics residual, which is, if when I compute the second derivative of my network and add in this omega squared x, if that's not zero, then that's a penalty. So, and again, I want negative and positive residuals to cancel out. So I'm going to square my residual and say that this is my physics loss here is I'm just going to take this residual from my differential equation and put this in. Okay. So now my overall loss, so our physics loss is going to require us to take a derivative of the neural network itself. So my total loss now is going to be loss of actually fitting the data, and we can minimize that the same way we were before. Now plus my physics loss, and again, if these are on different scales, we might want to parameterize exactly what the scales are going to do. And let's just look at what the chain rule of this physical loss is here, or the physics-based loss. So if I do my derivatives through, we don't have to walk through everything together, but we're doing the derivative of the residual squared. And then when I plug in what that residual actually was, we see that we get to the point where we're taking the third derivative essentially of the neural network. So we're going to take the derivative with respect, in this case, to time squared. That's just our acceleration term, and of the network parameters themselves. And so this is where, we'll get into it again, but this is where the choice of the activation function makes a lot of sense, that we need to be able to take potentially larger derivatives when we're dealing with physics-informed neural networks, and we're putting in these extra assumptions from our differential equations. Okay, so the key points to know is that the neural network needs to, in this case, to have up to the third derivative. And we need to figure out, okay, how do we actually compute these extra derivatives? So when we put in just a loss function, usually, PyTorch, Keras, any of these will compute the derivatives for us. It sort of knows how to do that. But now we're going to be adding in these extra derivatives. So I want to just make sure that everybody knows how to do this in PyTorch at least. Okay, so this is the slide that I was talking about before. The hyperbolic tangent has a shape. If we take the first derivative of it, we get this shape, right? And this has just continuous derivatives throughout. So we can always take these derivatives of the hyperbolic tangent. Whereas for the ReLU activation, this is really good for fitting lots of data when we just do it as sort of vanilla neural networks. But when we take the first derivative, it's 0 or 1, and there is no second derivative. So if we try to do a physics-informed neural network with this, it's not going to work very well, right? So that's just one of the key things to take away. It's not necessarily written in the literature, but or at least I didn't find it. But when I was trying this in practice, I just kept not being able to fit things, and it's because I was using not good activation functions. Yeah.
This is a slightly more general question. Is incorporating the knowledge through the loss function the only approach that's been used in physics-informed networks, or are there ways to embed physics into the network in other ways?
Yeah, there's absolutely ways to embed it into the network in other ways as well. So the physics-informed neural network itself, that paradigm is basically by changing the loss function. There are definitely ways to encode the physics into the network itself too. So in particle physics, I know one of the ways at colliders that we started doing this is especially looking at graph nets or point clouds. So instead of having sort of the way we used to do it is say, okay, we're going to sort all of our particles that we're seeing in the spray of this detector, and I'm always going to just look at the energy and the momentum of each of them, and that's going to be my input. It's just this long vector of of energy, velocity, energy, velocity, energy, velocity, right? For all the particles, and then do things like that. And that works, but it's not really using physics the best we can. And instead, we can actually represent these as four vectors themselves, and then do four vector operations within the network instead. So I know there's a paper by Tillman, Plain, and others where, yeah, the all of the operations within the neural network are specifically um, uh, valid special relativity four vector operations. And so, yeah, you can absolutely do that. And I think that that's sort of what I hope that everyone takes away from this, is that a lot of what we're taught as we're sort of, as physicists trying to get into machine learning, we're learning the very traditional ways of doing the machine learning, which is often fitting forecasting data or other things like that. Maybe computer vision data. And as physicists, we have either more knowledge or other things like that. And so we do want to be creative with how we build our networks, how we build our losses, really think about what is it that we're modeling, and do that, and use these tools of auto differentiation and the ability of neural networks to fit general functions to our advantage, but not be beholden to the computer science literature. Yeah. Great. So the other thing that, yeah, I want to, as I mentioned, that we want to do is figure out how to compute these derivatives using PyTorch, in this case using AutoGrad. So as we get into PyTorch, I think it's definitely PyTorch has very good documentation. This is just a clip from their documentation page. You probably want to have this open when we're doing the tutorial. But essentially, if we have our model, which is going to be our neural network here, we can take derivatives of it by just doing torch.autograd.grad of, in this case, this is the output of the model with respect to the time that we put in, and we create a graph, which means that that's how it's actually computing the gradients. We can do second derivatives just by plugging in that we're taking the gradient of now this, again, with respect to the time, the vector that we're putting in. Again, we're going to create the graph. And so we're going to use this in our labs to make sure that we're actually computing the derivatives of our of the neural network to make sure that we're going to enforce that the differential equation is fit while we're fitting the data. All right. So the other thing that we can add in, I talked about the fitting the subharmonic oscillator, the differential equation. We can also put in boundary conditions. So for instance, we know in this case that I want to at 0 time be at 1. So we're fitting a cosine. And so we're going to put those in. And let's just look at an example of what we can do with this. So it takes a little bit longer. We've got many more training steps to do this because there's now competing terms, and we have to fit the assumptions of having the different sizes of the loss, of whether we're looking at the fitting just these orange points. And so here we can see that we're only fitting the data. We only have observed data from these orange points. In green here, I am putting in, we're evaluating the network at all of these, but all that we're going to do is say, I'm going to put in time equals 2 pi or whatever it is. I don't need to actually know what the value should be. I'm just going to say, does it fit the differential equation? And by doing that, we can see that the network, as we're training, does a really good job of extending past where I have real data observations, and fits the whole series here. Okay. So with that, I hope we've whet everybody's appetite to get in and actually see how we can do this. Again, we're going to do this on just the simple harmonic oscillator because we all know the solution and we know what we want to do. So what we're going to do is build a feed-forward neural network in PyTorch. If you haven't worked with PyTorch before, it'd be a good example on how to do that. We're going to use AutoGrad to make sure that we're doing this should be an ODE, but we're going to put in the differential equation residual. I've got scheduled for 20 minutes on working this. So what I want you to do is go over to the Google Drive and work on specifically the O1, the notebook. Copy this over to your own drive, and you should be able to run things. I've got a lot of code in there, and specifically what I've done is put in spots where we're going to just fill out the code for different classes. So I've put in solution start and solution ends with some instructions on what you want to do within there. And to know whether you've got it right, I've got these assert statements in the next cells, uh, and these should pass. And if they pass, then you should be able to go through. And so there's, I think, 10 spots where I want you to fill out code. Otherwise, there's I'm going to take care of a lot of the details of simulating the data and actually doing the training loops. I just want you to focus on how do we actually do the physics informed part. If you don't want to go through and do all of that, I do have the solutions folder that has all of these filled in with how I did the code. If you do that, this notebook takes 2 minutes to run, I think. So, there's a lot to read through, but with the 20 minutes that we've got for the session, it's good to go in and actually take a look at, can we code up the feed forward network? How does that do its first pass? And how do I do the autograd? All right, so I'm going to move over to my notebook. Yeah, Jan.
Yeah, for those of you who attended the introductory module yesterday afternoon, you already saw how to create a local copy. But generally speaking, once you have access to the drive, if you right click on the three dots at the end of this, you should be able to get an option to make a copy. The format for those of you who are following the format of that's in the style guide, you would create a folder that's called local copy of Brown AI Winter School. For this particular model, it's not actually so necessary, but if you want to, this is module 2. So if you want to keep each class module separate. And again, if you have run into problems, post something in the question and answer.
So we should be going through this one. Yeah, it's about 10:50, and so at 10:10ish, I think, is when we should um, come back and move on to the next part of the lecture. And yeah, how are the sessions run yesterday, or like, do you want me walking through the notebook or just giving everyone time to?
I think giving people a little bit of time, but running through the steps that you want people to change is probably a good idea. Someone is saying that they get, oh, interesting. Okay, there are some people who don't have drive access. I will, if you're in the Google group that comes part with the registration, you should have access to the Google Drive. You may have to go in Google Drive to shared drives, and then you'll see that drive in the shared drives section.
Yeah, so yeah, well, be quiet for a little while.
Oh, interesting. Some people are seeing they don't get the copy option when you right click. Do you click on the three dots? I believe that's right. Let me,
Yeah,
I have a non-Brown account that I can try to replicate this from. Hold on.
yeah. If you want to share too, that might be better than me sharing from mine for that. I'm just looking through the Q&A as we're going. So there's a question about the physical interpretation of Lagrangian by the physics-informed neural network perspective. I'm not sure that the network itself is not necessarily working with the Lagrangian. You might be able to have it work with that. I've got the Lagrangian here just to help us get to the equations of the motion, or the differential equation that we're going to end up using. But yeah, it'd be interesting to explore if just using the Lagrangian itself can help inform the physics of it. That'd be really interesting. And then another question about the activation functions. Um, is there a fundamental reason to pick certain activation function for a specific kind of application in the same way as the loss function, or is it more of a phenomenological approach? Yeah, I think that that's uh, presume well a little bit of both, but more phenomenological. I would say that again, you're trying to um, at least for the output, pick the range of the output that you're looking at and the phenomena that you're trying to fit. Interior, it's kind of just I think whatever is differentiable, smooth, and keeps gradients for as we have many layers to pass through. Um, yeah, so I think more phenomenological.
So a couple of quick questions. For those of you who can access the drive, when you create a copy, make sure that it ends in IPYNB. Otherwise, when you click on it, it won't recognize it as a IPython notebook. So you may have to make sure that the file name has the proper file ending for Google to recognize it as a notebook, so that it will open in Colab. Um, uh, in terms of the choices, uh, are people still finding problems with the make copy? So I've signed in as my external Google account, and I have a make a copy option, which is what you want. It will prompt you for permissions, so you might have to hit OK a few times. Again, if you did the introductory module yesterday, you gave those permissions yesterday, and so it won't prompt you for it. But if uh, yes, sorry. Yeah, one of the weird Google features is that you can't copy a whole folder using make a copy. You have to actually make a copy of the actual notebooks. Apologies.
As you are working through the notebook, the first few just sets up the analytical solution for that we're going to be trying to copy and then get some training data just by sampling this. And then the first step is going to be actually defining the neural network. And if you don't have PyTorch experience, I do recommend going to the PyTorch documentation. They've got some really good tutorials uh, on building the neural network.
Apologies, Brian. I don't know if you answered this question while I was scrambling to answer the others. There's a question about if you have just a generic data set, uh, how do you figure out what physics to use? And I think that's a sort of deep question about whether physics inform networks. If you don't know the problem, what
Yeah, I think that's exactly what I'd say. If you don't really know the physics that's involved, I don't know how you could necessarily pick it. So I view these as yeah, trying to say when you have a data set that you know should be following some physics, whether it's fluid flow or whatever it might be, a simple harmonic oscillator in this case. We have more than just observations. We have our physics knowledge, and so we want to put that into it. Uh, and so this is a way to help us do that. If it's just a random data set, or maybe it's something like fitting a predicting uh, house prices in Seattle, or whatever it might be. Um, those aren't necessarily going to follow the same fundamental physics that I wouldn't know how to put those in.
can I ask if someone has managed to get to the damped harmonic oscillator example, if you just put a quick note in the question and answers, just to get a sense of how people are doing.
And hopefully you're not doing the damped one yet, because we'll get to that one
Ah,
next.
apologies.
Um,
Just getting
uh,
through this one.
yeah, so this one is really just hoping that we get through this. If you're still struggling at this point with about 5 minutes left, I'd say jump over to the solutions one and run it and read through it. Um, if you want, you'll have these to as references in the future. Um, and one of the key things that I want to point out in this notebook as well is that when we're doing our um, putting in the physics losses, we do have to have these different weights for them. And so, I've pre-configured it with where we're fitting the data with much higher weights than uh, the other values. But you can definitely try playing around with these. See if we don't put as much emphasis on the initial condition, or don't put it, or put more emphasis on the simple harmonic oscillator. As you're training the network, how does that impact the how quickly it fits the data? You can definitely see that it oscillates a little bit in its solution as well. Um, yeah, we end up then with these losses are vastly different sizes, in part because we're um, yeah, this is why we've chosen the weights accordingly. Yeah, right. Well, with no input, I'm going to assume then that people have at least gotten through where they want to, have asked the questions they want, and let's go on to look at some more advanced topics on what we can do with these. Um,
Yeah, a couple of people have already confirmed that they actually managed to make it through. So
Perfect. Oh, cool. All right. Um, Great. So I think one of the first things you might uh, say when you've done this is like, okay, why am I going to use a pen if I already know what the solution is? That, like, what we just did was a lot of work to do for something that we can already solve analytically. And I think that's true for this, and part of that's that we're trying to do it in a situation that we're all familiar with. Um, but I think it's also, broadly speaking, like, we are trying to use these in a situation where we do know the physics and we want to use the physics. And so there is sort of this underlying thought process overall. And so some of the things that I really think about this is that we can hopefully use this to get a parameterized solution. Um, and I'm going to work backwards through these. That what we want to work to in this session is how we can get a network that will fit multiple parameters at a time. And that we can do this even in situations where we don't have an analytical solution. Um, Once we have this idea of being able to have a parameterized solution, we can actually then use this to a similar methodology, at least computationally, to do the inverse problem. So say that we actually have observational data, and we know that it should follow some constraints, but we maybe don't know what the damping term is or what the viscosity is. That we can then use these neural networks to actually fit the data that way, and regress or infer what the values of some physical constant are. And that we can also use this for just parameter space exploration. So if we've got a parameterized solution, this can be a really fast surrogate model to then query the network across thousands of different parameter combinations, find some interesting phenomenology that maybe is really what we're trying to look for that we couldn't find in some high-res simulation, and then run a targeted high-res sim there to be able to learn something there. So we can view these as, they're not going to be perfect, but as hopefully a cheaper, fast way to explore a wide swath of area of regimes, and then go in and do a higher res, more computationally accurate solution after that. In the next session, I'll discuss how some of this is done actually in industry. So to help us build up to all of that, let's just make our simple harmonic oscillator a little bit more complicated by adding in a damping term. So now we've got the gamma coefficient here, which is going to damp out the oscillations, whether it's due to friction or anything like that. And so now when we go to actually come up with our analytical solutions, one of the things that we're going to be concerned about is the damping ratio of gamma over 2m. And we're going to compare this with what the before we just had is the frequency. Now it's going to be the natural frequency, what it wants to oscillate at if there was no damping. I'm sure we've all seen these before. Again, there's different regimes for this. That if the damping term is less than the critical frequency, that this will oscillate, but with decreasing amplitude. It can also be critically damped where they're the same. This is the fastest return to equilibrium. And if it's overdamped, essentially it's damping the motion so much that it can't return to the decay as fast as it wants to. So it's slower decay, but then there's no oscillation. Ricardo, I will try to get to your question at the end, but essentially, yes, there are ways to do things with atmospheric physics as well. And so if we look at these damping regimes, again, just for the damped harmonic oscillator, we've got the underdamped, which oscillates, and then the critical, which is the fastest to go to 0, and the overdamped is so damped that it can't actually move as fast as it wants to. Okay, so we're going to do the same thing here now. We're going to fit our physics-informed neural network, and to see how we can do this. I want to we're going to do basically the same thing. So we're going to put in our physics residual now has the damping term in there. Otherwise, we're going to just do the same initial conditions. And so since we've basically already done this problem, I want to show that we can do this actually in the regime where we don't even have observed data. So let's actually say that we're going to now take out our physical data. And so we don't have a data loss term. I'm not going to put in any of those orange dots that I had before, which were our predictions or our actual observations. And we're just going to instead sample across time and force that we obey the simple harmonic oscillator everywhere here. And then I've also got some boundary terms that are not really showing up, but along time is equal to 0, we're going to try to enforce that we start at 1 and that the derivative is 0. All right, so we can do the same sort of thing. And now when we train, we can see that we can actually fit these different terms. And so I think this one's going to keep looping. But with this physics-informed neural network, even though we haven't given any data, we're not doing the mean squared error anywhere. By just fitting the differential equation residuals, we're actually able to really get these solutions across all of the different damping regimes. And so this is great. We now have that we can predict that x is a function of time, which is just our neural network given our parameters. And so this seems really powerful, right? It's sort of again showing that we can just simply put in the physics here. And of course, there are limitations as a question gets to, and we'll get to those as we go throughout. But one of the key things about this is that right now, as we have this set up, that this is only solving the differential equation it's not even really solving it, but right, we're getting the predictions here for one particular value of the damping and frequency. And so if we want to change those, I can't do that. So if I train my network on d is equal to 2 and omega naught is 20, and say want to evaluate uh, across different regimes, well, my network is really only a function of time, and so it's going to do the same blue prediction everywhere. And so, okay, I'm showing the different ones with different mean squared errors. Uh, it it's really in some sense nonsensical because I only have this one blue prediction everywhere. And so what I want us to now try and think about is, okay, well, how can I actually fit a family of solutions and parameterize my neural network to be able to work across all of this? So again, when we started, we were using saying that our x is a function of time, and so we made a neural network with one input, time, and it had lots of different internal parameters. Uh, and each time that I changed d and omega naught, we'd have to do a new training. But we can also just say, well, let's actually make d and omega naught also inputs to our network. And now for the same input or for the same internal network parameters, we can train on this, train across a wide range of d and omega naught, and then hopefully we'll be able to fit anything within there. And so there are a couple of caveats to this, that when we add in extra input parameters, that does increase the size of our network. If we do this across a really wide range, we might need to make our network bigger or more complex to try and fit different regime changes. And let's actually just see if I can. Did that not run? Oh, maybe this. Oh, this is actually my solution already. So we can see here, once I train this across different values, now for the same network, I can just say, okay, I've got my network. I give you any d and omega naught and time, and I can just plot out what the solution is. And we can see that it's fitting both the underdamped. I guess these are all underdamped, but we've got quite different regimes here. It can also scale to the critically damped and underdamped or overdamped. And you might say that, well, this one's not actually a great solution, and that gets to the point where I was saying before that we can view these as surrogate models to allow us to hopefully explore lots of reasons of parameter space and have a decent estimate of what the physics is going to be at that location. Go find somewhere interesting, and then go and do the analytical solutions from there, or an actual more rigorous computational differential equation solver in that case. So for a parameterized neural network, again, what we're doing is really just changing the input, and we have to sample when we're training across lots of different regions. In this case, we were doing it with no observed data, and that actually makes things in some sense easier. So just every time that we're in each batch of our training, we can just pick random values of t, d, and omega naught and ensure does it fit the differential equation there. So that's pretty powerful. There is, compared to the standard pin, it does take a larger network and higher training costs, but it builds a reusable solver that in principle we can use anywhere. Okay. Any quick questions about parameterized networks? I think this is a really powerful thing that we should use in physics more often. I know that it was introduced into the high energy physics regime. When I learned about this, it was, we wanted to look for supersymmetry at one mass and then maybe at another mass. And we have to really train the network across each different mass range, and that doesn't make much sense. And so if we parameterize that, then you can get better results, and it better learns and generalizes the physics across all of this and does a good job of that. So once we have that idea of being able to say, well, let's actually just change what we're fitting, we can get from to the point of doing the inverse problem as well too. So everything we've done so far is saying, given that I have the differential equation and some parameters and input and output conditions, let's go and find the solution. Well, the inverse problem is saying, okay, I know that I have the physics that I want to fit, and I've got some observations, and I actually want to figure out what those parameters are. So in this case, maybe what the damping term is. And so we can do this in a very similar way. So instead of having the weights of the network be learnable parameters that we're optimizing, we're now just going to make, in this case, mu. I'm calling it mu instead of gamma because it's the thing that we're fitting and it's not the true value. That we can optimize this right alongside the neural network. So how does that work in principle? Well, again, if we think of the loss as just the negative log likelihood of or the negative log likelihood, we're trying to maximize the likelihood, in this case, of fitting our observations, and that we know that we want to fit the physics data as well too. So in this case, my physics loss is still just the same differential equation residual, and now I've got my data term here. And if my function is now just x as a function of time, but I have mu as something that's going to be changed as I'm taking derivatives, then as I fit the function, I essentially am fitting the data and pushing it to the known physics. So that's how I can regress out mu. And we'll see this in the notebook, how to do that better. Okay, there's some questions before I move
Just
on. Yeah,
the new question has to do with whether Lagrangian physics informed machine learning is a subset of physics informed networks, and are there technical differences between those methods?
I'm not sure, unfortunately.
I,
It,
I suspect it's a question of how you encode the equations and the physics laws.
yeah,
So if you encode it in the Lagrangian, that's one way of doing it.
right,
Then you encode the equations of motion explicitly. And the advantage there, I would imagine, is that the equations of motions generalize. So your
right,
code is essentially the same, and all you're changing is the Lagrangian that you're fitting in.
right, yeah. Um, and I guess just to the question above as well, the limitations of pins is in some sense that we do need to have the boundary conditions, or that we're trying to solve it for, even as we're going to this parameterized version, that we are still sort of in some sense, um, the differential equation part itself is maybe easy to code in here, but coding up the boundary conditions can be hard. So one of the cases that Darsh and I had been looking at was, say that we were working with a car manufacturer, and they wanted to simulate lots of different shapes of their car going through a wind tunnel, right? So you could do air fluid flow around the car, and we know that's going to do Navier-Stokes, but trying to actually encode exactly, well, how does the boundary condition of this car change, and how can I parameterize that? There's other solutions that sort of bypass that, but still trying to model the physics in other ways, called neural operators. And so I think that's probably, depending on the scenario, a better way to go about doing things, depending on what the problem is. And so that's not exactly getting into Lagrangian physics informed neural networks, but yeah, so I think again, it is in some sense, it depends on exactly what you're trying to solve, and what the problem is. And so again, one of the key things of these lessons being, really think about what it is that you're modeling. Don't just take the literature, but be able to have these as tools and do, in some sense, whatever you need to with them. So to get to now something just a little bit more complicated, we're in the notebooks. I've got a tutorial on doing Berger's equation, which is a subset of the Navier-Stokes. So in this case, we've got the Berger's equation is it's a fundamental partial differential equation that appears in fluid mechanics and material science and applied mathematics. It's a simplified model of the Navier-Stokes, and it the equation captures the essential nonlinearity interactions in the fluid dynamics while remaining simple enough to study analytically and numerically. So there's an advection term, which allows the fluid particles to carry momentum, and this provides nonlinear steepening. And then there's the diffusion term, which models the viscous dissipation and smoothing. And so there's lots of different phenomenology along here. When there is small viscosity, we can get shock formations, and so we can see that the solutions are going to steepen. We get very high derivatives here, and so what we want to be able to see is in these complicated scenarios, can we still use a physics-informed neural network in these cases, do a partial differential equations with all these nonlinearities in it. And so I know that Darsha contributed a lot of this, and so I'm definitely not an expert in this. But to give you a little bit of intuition on this equation, if I look at just if I sort of um, ignore the viscosity term and have just the time derivative plus the field and the x derivative is equal to 0, what that's essentially going to say is that the it leads to nonlinear steeping. So the field transports itself, and so when there's regions of high values, it's going to happen even faster. So essentially, the values up here are going to move to the right even faster than the values over here. If it's negative, it's going to move to the left, and the more negative is the more it'll. So that's where there's the steepening that's going to happen. And conversely, if I'm doing all this where I've put in the initial condition of a sine wave, just to be able to see what's going on. The other term is dissipation, similar to a heat equation, and so it's going to want to bring things to uniformity, and so it's going to dampen out any of our gradients and decay our amplitudes. And so we essentially have the combination of these two different terms competing with each other. And we have different regions of high viscosity where the diffusion is going to dominate, and we get sort of smooth diffusion and it collapses like this. There's medium regions where we start getting to what looks kind of like shock, but it never quite gets there. And then at really low values of the viscosity, we can get some pretty sharp peaks. It's not technically a shock unless this is v nu is equal to 0, but it gets pretty close to it. Okay. So let's take a step back then. Okay, this is the physics of what's going on, but how are we going to do this with a physics-informed neural network? So now we have two inputs. We have position and time in this case. We're still going to have multiple layers with many neurons, and our output is just going to be the field value. So our function is going to be the neural network is u of x of t. Again, we could parameterize it with nu if we wanted to. I don't do that in the notebook, but feel free to take that as a challenge. And the real only difference that we're going to need to do here is that when we're taking our autograd derivatives, we're going to have to take derivatives of x and t separately. We're going to enforce Dirichlet boundary conditions, and we may need to sample more. And so when I say that, again, in the notebook, I'm not going to work with any observed data, but what we can do now is we've got a 2D data set, is that I have boundary conditions spaced along the y-axis here. That on my boundary conditions, I'm going to say that I've got fixed boundary conditions, and I always want these to be at a value of 0. And so that's what these are going to represent. And we could sample these lots if we wanted to. And then I also have initial boundary conditions, which is my sine wave that I'm putting in on these red squares. And then again, each time that we're going through the training, we can just sample lots of different random points within here and see that we're enforcing the physics differential equations are satisfied within these. And I mean, in the notebook, I've got a study of what happens if we use different values or how many sampling points we're using to fit the differential equation. Okay, so with this, I think we can jump back into the labs. And so there are two separate notebooks that I want you to look at. So the first one is looking at specifically the damped harmonic oscillator. This one, we're going to implement the physics-informed neural network. I want you to look at how we can balance the different losses, but the key points that we're looking at in this one is how we can build a parameterized neural network. And I think that again, will help you across a lot of different regions that you're doing things in your physics studies, and how to do the inverse problem. So that's the key learnings of looking at the damped harmonic oscillator. Then there's another notebook on the Berger's equation, and for that, we're really trying to see how can we fit the network across these different regimes. What does it take to do it? And in particular, we changed the training strategy a little bit in here. We're not just fitting with Atom; we fit with Atom, and then once we get to a close point, we do some extra fitting on top of that. So um, the harder our equations get, the more that we have to start, really worrying about tuning and getting things to work well. Um, so yeah, I think we can jump back over to the notebooks. Uh, Say take about 20 minutes on each of these. The amount of code that you have to do is smaller. It's again really just putting in those derivatives and the feed forward network. I've got the rest of the code in there, but please play around with some of the different explorations if you're interested. And so, yeah, I've got 40 minutes roughly allotted to the rest of these. We can work on any of the notebooks now that are of interest.
And again, as before, put any questions in the Q&A.
Yeah. So one thing I'm remembering now, actually, in the parameterized network, when we're sampling our data, in this case, we are actually are um, enforcing that it's going to be in the underdamped regime. So if you've gone through the notebooks and want to play around with that, you could also see if we can make the parameterized network work across both overdamped and underdamped regimes. The question about the relativistic Burgers equation, uh, I don't know if a pin can solve it effectively or not. Um, I think that it'd be interesting to try. I think it should be able to do it. I would in the um, references, I've got some of the original pin papers, and then I'll be talking about in the next section um, where people have the same group has done the full Navier-Stokes equation with a pin, and so I think the shocks and all of that there make me think that you could be able to do it, but um, I think one of the key things is that they had to do a lot of parameter tuning, hyperparameter tuning to get it to work right, and really worrying about how well the different loss weights compare to each other. So um, I think yes, efficient is is a question. But I think it'd be really interesting to see if you can do it, right? And so again, the if you can enforce the physics as you're doing it, then that's sort of the goal.
Yeah, I would expect that the same issues that come up with in the Burgers equation with sort of shocks and very quick discontinuities will show up in the training if you're allowing arbitrary values of gamma that you will have to train very densely at high gammas.
Yeah. Yep. And so I think one of the things that I don't quite get to in the notebook as well too, and yeah, we can move over to the Burgers equation notebook now, uh, is that we can pretty easily, like, we're computing the residual at each point. That's how we're actually optimizing the network. Uh, but it would be pretty easy to as we're training. So here's just a comparison of sort of the different regimes of um, no shock to closer to a shock, and we see that we have more error when there's a shock. Um, that as we're sampling all of our points, let me bring back up the. Uh, sorry, one moment. So when we were looking at this plot, so this is how we end up training the network here. So each iteration through, we're essentially drawing new random blue dots. Um, but we know the residual at each one of these, and so you could work this out to say, okay, well, I know the residual is higher at closer to where the shock is forming or near the shock, sample that region more in the next iteration. And so there's adaptive learning techniques like that could be applied to the same formulation, just changing now instead of changing the loss, now we're changing how we're sampling during training. And so I think that would be a pretty effective way to try and get any of that as well too. I don't have any papers specifically on that, but I think that general idea should work um, pretty well for some of that. And so again, trying to take some techniques from computational methods as well too, to doing sort of adaptive grids or adaptive sampling in this case. Okay, unless there are any last objections or questions on the notebook right away, I'm gonna jump back into the last part, which is looking at some examples in industry on how these are being used. So we've completed the last labs, looking at the damped harmonic oscillator and then Berger's equation, and the damped harmonic oscillator lab. Now you learned how to encode a second order differential equation into a neural network's loss function, used automatic differentiation to compute derivatives and fit the model to both data and physics. And you saw the network could learn the solution, but also infer parameters like damping and frequency. And Berger's equation, you worked up to a partial differential equation. You handled spatial and temporal derivatives, balanced the data and physics loss terms, and saw how pins can solve problems where traditional methods struggle, especially like where the data is sparse or noisy. And these same building blocks are used in state-of-the-art research. And so in this section, we're going to look at how the techniques that we just practiced, encoding the physics and the loss using auto differentiation, balancing the different loss terms, and inferring hidden variables are being used to solve problems right now. So let's dig in. So in this first example that I've got, and again, none of this is my research, and I only am a little bit familiar with these, but I think that they're pretty useful overall. So in this power systems paper, it's a really cool example because it's a direct extension of what we just learned. So the swing equation, which is what they fit here, governs how generators behave on a power grid. It's essentially the same oscillatory dynamics that we worked on in the first lab. And so if we think about what a generator rotor is, it's like a pendulum that wants to stay synchronized with the grid at 60 hertz. And when there's a disturbance, like potentially a sudden load change or a fault, the rotor swings away from synchronization. And so the question that grid operators face is, will it swing back and to sync, or will the system go unstable? So there's this is a big problem, and classical methods to solve these differential equations numerically are very accurate, but they're slow. And so what these authors wanted to look at is, in the pin approach, can we train once using all of the physics and then be able to just get the answer? And they found that they could actually get the answer 87 times faster than doing the full differential equation solver. And for the operators, that's the difference between having time to react and being able to respond in real time. And a cool part of this paper is that there's actually the inverse problem too. So they have to infer unknown parameters like the inertia constant or the damping coefficient from the measurements, just like what we did in our oscillator problem. So just to dig in a little bit more into this, so here's some of the specifics. So the swing equation looks intimidating, but it's really just Newton's second law for rotational motion. M is the inertia, how much the generator resists changes in speed. D is the damping. Sorry, yeah, okay, here's the equation here. D is the damping. It went away. D is damping on how quickly the oscillations die out. PM minus PE is the net power, the mechanical in minus the electrical power out. Notice that this is a coupled ordinary differential equation system. The frequency deviation omega determines how the rotor angle delta changes. and the power balance depends on delta through the electrical power, PE. It's interconnected just like real physics tends to be. And the 87 times speedup comes from training the pin once on the underlying physics, then using it as a fast surrogate model. How this connects to what we've done, if we look back at our labs, the table comparing the simple harmonic oscillator to the swing equation, the position becomes the rotor angle, the velocity becomes a frequency deviation, and the mass is the same as the inertia. And the physics is really the same, the oscillatory dynamics around the equilibrium. And what changes is the application domain and the stakes. A poorly tuned oscillator simulation is a bug, a poorly controlled power grid is a blackout. So the skills that we looked at today, encoding the ODEs as the loss function and using autodiff for derivatives, inferring parameters from spatial measurements, these translate directly to this sort of work. So this is pretty cool. All right, there's another example that we've got doing cardiac activation mapping. So we switch over into medicine. So atrial fibrillation affects millions of people. It's when electrical signals in your heart's upper chambers become chaotic. And to treat it, cardiologists need to create activation maps. Where and when does the electrical wave travel through the heart? And the problem is that you can only put a catheter in a few spots, or maybe 10, and get 50 measurement points to reconstruct what's happening in the entire atrium. And the traditional interpolation just draws smooth curves between the points. And part of the problem is that the heart tissue isn't a smooth function. There's fast conducting pathways and slow fibrotic regions. And this paper asks, what if it can encode the physics of wave propagation into the neural network? So they use the Eikenall equation, and it says that the gradient of the activation time is equal to the inverse of the conduction velocity. It says that waves travel at speed, and that speed varies across the tissues. So T of x is the activation time at a point x, and V of x represents the local speed of the wave at the same location. And so here's a connection back to what we worked on. If we notes are going the wrong way. So the Eikenall equation is elegant. It says that the magnitude of the gradient of the activation time, it's how steeply the timing changes as it moves through the space, is equal to the inverse of the velocity. Fast regions have gentle gradients, slow regions have steep gradients. So the researchers here actually trained two neural networks simultaneously. One predicts the activation time t, and the other predicts the velocity v. And here's a key insight into what we had to work on as well, is that they only have data for the activation time when the sparse measurement actually takes place, but they don't know the velocity. The velocity field here is learned entirely from the physics constraint that they're putting into the differential equation. And so this is a powerful inverse problem that the network discovers the conduction velocity field without ever seeing velocity data directly. Physics is filling in what the measurement itself can't provide. And so let's connect this with the experience that we have. So we solved the Burgers equation. They solved the Eikenall equation. It's a different PDE within the same framework. But both have to use the autodiff for the spatial derivatives. Both balance data terms against physics residuals. And the new concept here that they have to use is this active learning that I mentioned, that I talked about but didn't put into the notebooks. They train an ensemble of 30 networks using the same architecture at differently random initializations. And where the networks disagree, that's where they know that there's high uncertainty. And so they sample those regions more in the next measurement. And so essentially this is closing the loop. From a physics-informed prediction, you get higher uncertainty, and this thing, you know where you need to reduce the uncertainty. So then that's where the doctor is going to measure next to help fill that in. So it's asking where the doctor should put the catheter next. Great. Let's look at one more example. So this is doing the full Navier-Stokes. Ooh. Um, great. And so this is the most ambitious one that I'm looking at here. This is the full 3D incompressive fluid dynamics equations. Drives weather, aircraft design, blood flow, everything involving fluids. And this paper from Brown University takes pins into the turbulence territory. They simulate channel flow at Reynolds tau of 1,000. It's fairly turbulent with chaotic eddies across wide range of scales. Classical computational fluid dynamics requires careful mesh generation, time stepping schemes, turbulent models, and here with the NSF net, they just encode the equations and let the gradient descent figure it all out. What makes this paper special is the hidden pressure concept and the velocity pressure formulation. The network outputs velocity and pressure, but you never give it pressure data. The incompressibility constraint, divergence and velocity equals zero, implicitly teaches the network that pressure must be pressure emerges from the physics itself. Uh, And so, the equation itself is complicated, but the left side is the acceleration, both the time derivatives and the nonlinear convection term. The right side is the forces, pressure, gradient pushes fluid out, viscous terms smooth things out. And notice that this is similar to the Burger's equation that we solved. We have the same nonlinear advection term. This what we did is warm up. This is the full real deal in 3D. Um, and so the paper tests out two formulations, velocity pressure, which outputs the field value V, W, and P, and vortices velocity, which outputs velocity and the curl of the velocity. Interestingly, the vorticity formulation is more accurate for laminar flow, but only velocity pressure works for turbulence. These details matter when you're pushing into hard problems. And so to the bridge from the lab that we did is that we already understand the hard part, the nonlinear u times the du dx term. It's the same physics. The momentum is being carried away by the flow itself. You add pressure and coupling to get to 3D, and suddenly you're doing computational fluid dynamics. The hidden state concept is really pretty profound within here. In traditional computational fluid dynamics, pressure velocity coupling is a major headache. You need special algorithms or projection methods. And again, here with the network, they sidestep all of that. The network outputs pressure. The divergence-free constraint in the loss forces pressure to take physically consistent values. No boundary conditions on pressure were required. And so then one of the last things is that loss weighting really matters a lot here. They spend a significant effort on the paper on this, manually tuning the weights to depending on the problem. And so again, when we talk about pins, really look like they're really powerful, but there is this fitting them can be challenging. The dynamic weighting schemes here that they use, they have to adjust during training. So we scratched the surface, but real applications require a lot of depth to get this to be tuned well. All right, and then I'll take a step back out and zoom way out to some of the Microsoft projects that are going on. I'm not directly involved in any of these, but I think they're really interesting. Neither of them are using pins directly, but I think they're still worth talking about in the session to again look at some of the broader ideas beyond just the changing of the loss function itself. So the Aura project is Microsoft's foundational model for weather predictions. Um, it's a 1.3 billion parameter model that's been trained over a million hours of atmospheric data, and it predicts the weather 5,000 times faster than traditional numerical methods. This isn't a pin, as I said, in the strict sense. It's not encoding the partial differential equations into the loss function, but it's deeply physics informed in spirit. It learns the outputs of physics-based climate simulations. It uses a 3D Swin transformer architecture, which represents the spherical geometry of Earth. And this came from the same research group. And so I included this here because it shows where this field is heading. So we can use pins for specific problems, but if we want to, the way that a lot of the field is going is getting to foundational models. So here they're trying to learn the physics implicitly from massive simulation databases. And both approaches work, and the right choice depends on the data availability and the compute budget that we have. So just a couple more details about this. Um, Again, I said that it uses transformers. The 3D swim transformer gives the attention mechanism, which is useful for data that comes in series. Uh, and so that helps it respect the spatial structure. And the swim part means that it uses shifted windows, which efficiently handles the global nature of weather patterns. And the insight that they have here is that the weather variables have different spatial and temporal scales. So temperature varies slowly, wind changes faster, clouds are patchy, and they use an encoder decoder structure that handles the heterogeneity of processing different atmospheric layers with appropriate resolution. And so they do this by a clever training where they pre-train on lots of diverse data, including low fidelity climate simulations. And once they've done this, they then fine tune on higher quality analysis products. And they find that the diversity matters much more than the quantity. So just using more isn't better, but using a wider range of things is better. And so that's again trying to get it to be able to generalize is really important. That it can learn sort of the base physics everywhere, and then learns the physics really well in a couple of high fidelity simulations. Um, all right, and so this is a conceptual jump from pins. Here they're using these neural operators. So while we trained our pin on a simple harmonic oscillator, we got a network that represent one specific solution. And when we changed the initial condition, we had to retrain. So we tried to go about changing that by doing the parameterized neural network. And as I mentioned then, that it's still while you can do that, the getting to different boundary conditions and trying to parameterize those can be hard. And so that's where these neural operators come into play. So there's neural operators like deep O-nets or Fourier neural operators. They learn the solution operator itself. So they take basically instead an initial condition. So where the weather is starting at, where the atmosphere is at now. What for us it could have been where the initial harmonic oscillator starts as input, and then they output the solution down the road. And so the trained model itself is handling is learning all of the physics within that. So the way that they do this is they feed in today's atmospheric state and they get tomorrow's weather. You feed in at a different starting point and you get a different forecast. And so in this, the training cost is really massive, but inference is really cheap. And so that's one of the trade-offs that we always have in this. Okay. And finally, one more cool example from Microsoft is battery discovery. And so finding new battery materials is really hard. You have a combinatorial explosion of possible elements, crystal structures, and compositions. And so to test on each one of these takes months, and simulating each one with quantum mechanics takes thousands of CPU hours. And so what they did here is they used a surrogate model, as we've talked about, to learn to predict the material properties from structure. So that M3GNet and GNOME take similar approaches to train on hundreds of thousands of quantum calculations, then screen millions of candidates all within hours. And so that, if we want to look at this from the physics informed angle, they're not really quite doing physics in the learning itself here. But they do use that the force is equal to the negative gradient of the energy. That's encoded through the automatic differentiation, exactly the way that we did in the pins. So the network predicts the energy, and Autodate gives you the forces, and you have a potential energy surface that obeys the fundamental physics. And so to make a connection just to what we did with the pins, you enforce the differential equation as a soft constraint in the loss. Here in their networks, the fundamental physics relationship is the forces and the gradients of the energy, and that's enforced through the architecture itself. You predict the energy, you differentiate, and then you get the forces, and then they do another training on both. And so both of these, in fact, are surrogate models, or the pins that we have are surrogates, and then these solving the differential equations. And here they're using this as a surrogate to solve the Schrodinger equation. Both are expensive simulations, and you can replace the expensive simulations with neural network inference. When they did the battery discovery, they trained on the surrogate physics simulations to screen millions of different candidate materials. And they filtered out to the most promising ones, and then they were actually able to go and synthesize these in a test lab. And this is really important, that we don't necessarily want to just trust the machine learning results overall, but it allowed them to take such a wide range of materials. They found a promising ones, and they were actually able to go and make it in the lab, and now they're able to have a battery that uses much less lithium. And so this has been done in practice, and it's pretty cool with that. So yeah, I think there's a lot of promise to these general ideas, even if it's not strictly just changing the loss function itself. All right. So just to wrap up, I think some of the things that we've talked about today is that when we're sitting down and saying, "Hey, I've got this problem and I want to use a neural network to solve it, or I may want to use this as a modeling," like really think about what assumptions are you making. Can we encode more information in loss functions, or when we're choosing our loss function, what assumptions are we making? A lot of what the actual tools like PyTorch or Keras, anything like that, is giving us is good auto differentiation, and uh, we can use that as a tool as well too. So we looked at implementing pins for ODEs and PDEs, how we can do this using collocation sampling without actually having observed input and output data. When we did this, we had to really balance the different loss components. So we had the data loss, the physics loss, the initial condition losses, et cetera. And when you have all of that, there's a lot of tuning that's going to need to be done. We looked at a little bit on when to use pins and what some of the underlying problems can be with those. And so this field is rapidly evolving. I think with some of the limitations, we're not necessarily going to always use the pin exactly by itself, but there are these other ideas that we looked at of using neural operators or graph neural networks. There's other ways that we can, as somebody asked earlier, of actually try and put the physics into the network structure itself. And so I think that's definitely worth looking at depending on what your problems are. Within any of this, we can try to use techniques like adaptive loss weighting, other things like that. Use transfer learning to do sort of initial tuning and fine tuning. And we looked at some of the different applications that this could be used for. So yeah, within these notebooks, there's other explorations that you could do to try and work on some of these problems. But otherwise, yeah, I'm open for any questions in the last 10 minutes or so of the session. And definitely looking for any feedback.
Well, thank you to Ricardo for that cool note on quantum control.
Yeah.
And also a quick reminder that these notebooks, as registrants, you will have access to these notebooks basically for the whole rest of the year. So you'll be able to, like, there is not a huge hurry for you to try modifying things.
And I should be able to uh, give me on, or somebody my slides as well too, if people want them, just for some of the references that are in here too. I tried to put references in all the notebooks, but I don't know if they all map one to one. Um, yeah.
Thank you, Brian. Yeah, I think what we'll do is we'll put them in the Indico, so when you're
Yeah.
registering for them, you can actually access them from there on some timescale. Again, you'll have access to that for the whole year as well. I will say if there are no questions, we should thank Brian again for this fantastic presentation. Really cool stuff. I wanted to remind people that we will be meeting again at 2 o'clock for the second module of the day. Matt LeBlanc will be talking about optimal transport in collider physics, particularly in LHC physics. We'll use the same channel, although we'll close this channel and then reopen it around 2 o'clock. So thank you, everyone, and enjoy your break. And we'll see you in about an hour and a half.